Hey class, Mr. Mojan here with a video introducing two important theorems in calculus called the intermediate and extreme value theorems. They're two of the first theorems that we look at in calculus, which are called existence theorems. There are several we'll see in our exploration of calculus. They're existence theorems because they don't necessarily tell you what a certain function does at a certain place. It just tells you that a certain value must exist subject to certain criteria. They guarantee the existence of some number, and it describes why or where that number could exist. It doesn't really tell you how to find it, simply that it does exist. The important thing to know for the moment is that these are two intuitive ideas that are limited to continuous functions. So because continuity is something that's sort of intuitive to us, because time and temperature and other elements that are native to our living on Earth behave continuously, for this reason the behavior of continuous functions kind of feels natural, and as such, even though they have sort of complicated terminologies to them, the actual nature of both of these theorems is very intuitive, as we'll see. So let's dive into the intermediate value theorem first. This is the statement of it, which you definitely want to get written down. It says that if f is a continuous function on the closed interval ab, and w is some number in between f of a and f of b, then there exists some number c in ab such that f of c is equal to w. Now, most of you may hear that and you have no idea what's going on. Let's look at it bit by bit with a picture. So first of all, we're limited to a continuous function on a closed interval that spans from a to b. So I'm going to mark a here and b there, and over this interval my function must be continuous. It might be continuous everywhere, but it certainly needs to be continuous on this interval. And w is some number in between f of a and f of b. The key thing to recognize there is that these are y values, or outputs. These are what the function is mapping to. That means that w, since it lives in between them, must also be an output. So w should live on the y-axis, so to speak. So I have some kind of function on this interval. I'm going to happen to make it a nice continuous curve, a smooth curve, actually a differentiable curve, but keep in mind this could be jagged and it would still be true. But it's just a nice picture to draw. So I have two values here, f of a and f of b, which are generated by the input and output respectively. So this number right here on the y-axis is f of a, and this number right here on the y-axis is f of b. And the number that we're mentioning, w, must live in between those based on the hypothesis here. If it's continuous and w is some number, then, for the conclusion, there exists. So that's a term we use a lot in math. So there's a nice symbol for it, which is a backwards C, which is sort of strange. There exists some number c in the interval ab such that f of c produces w. So what does that really mean? That means in order to go from f of a all the way up to f of b, or vice versa, all the way down to f of b, in any case, I must pass through every single one of these numbers. And that means that w, just one of those many numbers, must have some value in between a and b that generates it. Because c is in between a and b, that tells you that c is an input. And it says that f of c must produce w, because the coordinates of this point must be c, comma, f of c, and in this case f of c is w. So it says that in order to go from f of a up to f of b, or vice versa, you got to pass through everything in between, or intermediate to those inputs. And the value that produces that output of w must also live in between a and b, because you can't get from here to here without going through every number in between, no matter how you connect those two dots. The important thing to keep in mind is that the intermediate value theorem, which hopefully you get a sense of it being fairly intuitive, is limited to continuous functions. Let me show you a counterexample to verify that discontinuous functions don't apply. Let's say you have the Golden State Warriors and they score 26 points at the end of the first quarter, and then later they have 48 points. So over time, you could imagine that at the end of quarter one, they have 26 points. At the end of quarter two, at halftime, they have 48 points. So naively, one might say that, oh, well, that means they must have had 30 points sometime during the second quarter, right? But keep in mind, scoring in basketball is not continuous. You go up in increments of either 1, 2, or 3 points, depending on what kind of basket or free throw is made. So you have these sudden increases, and you have a discontinuous graph. In other words, the Warriors may have gone from 29 points and then someone scores a basket and they move up to 31 points. They did not pass through 30 points to do that continuously. They didn't have 30 points and scoreboard at any point because this is not a continuous scoring system. So keeping that in mind, let's look at an example of applying the intermediate value theorem. Use the intermediate value theorem to show that this function has a 0 or a root in the closed interval 0, 3. So the first thing to do is to understand why the intermediate value theorem applies. So we need to state that f of x is continuous on 0, 3. It's actually continuous everywhere, but certainly continuous there because it's a polynomial. There's no numbers you can throw in here to break it and create a discontinuity. So polynomials are always continuous, and that's always a safe assumption, but it is something you need to state from the outset. It is continuous, and therefore the IVT applies. The IVT applies. Why? Because it's continuous. That was part of the hypothesis, right? So now let's look at the end behaviors. What is f of 0? F of 0. Well, if I plug 0 into this thing right here, I'm going to get 0 squared minus 6, 0 plus 8, which is 8. And if I plug in the output, which is 3, or the endpoint, which is 3, and the output that I get is 3 squared minus 6 times 3 plus 8, that would be 18, and that would be 9. 9 take away 18 plus 8 should give me negative 9 plus 8, or negative 1. So here's where a picture might help. At 0, I've got 8, and at 3, I have negative 1. So that's 8, it's 3, and I have negative 1. So because I know this is a parabola, I kind of have an idea of what it looks like, but even if I didn't know, if I just knew it was continuous, that's not a function, even if it were something peculiar, there's no way to go between those two dots without passing through every number in between. And the key thing to recognize here is there's a specific number in between negative 1 and 8 that happens to be our number of interest, which is 0. And we're sort of getting to the point here, right? So, how do we actually state our conclusion? That since we went from 8 to negative 1, we've got to pass through 0. By the intermediate value theorem, there exists some c in the interval 0, 3 such that f of c equals 0 because let's see, f of 0 was 8, right? And f of 3 was negative 1. And in between those, we've got to pass through everything, right? So f of c must be between negative 1 and 8. Because these could be inclusive as well. And because 0 is between negative 1 and 8, inclusive, this statement must be true. So because the endpoints create these two boundaries, basically, below and above, I've got to pass through everything in between, there must be some number that creates 0, which is what I want. It doesn't tell me where it is. It simply tells me that such a number must exist, hence the idea of an existence theorem. By the intermediate value theorem, reading the black here, there exists some number in the interval that creates 0, because on one end, I'm too low, on the other end, I'm too high, which is what this is saying mathematically. Now, how to actually find this number is something we'll actually see in class. So keep in mind, it simply guarantees the existence of such a number. It does not really tell you where it is specifically or how to find it. That's something you gotta do. It's a little bit more beyond the scope of this video. But for now, that's the intermediate value theorem. Let's look at the extreme value theorem, along with an extreme image here. Very cool. Also an important thing to get written down. It's a very simple idea, but sometimes the language can get in the way of that. But let's take a look. If you have a continuous function on a closed interval, then the function must have a max and a min value. That may seem intuitive enough. There's some number that's real big and it's bigger than all the rest. That's a max. And there's some number that's way smaller than all the rest, and that's called a min. Which is to say there exists some c and d in the interval. So those are, again, inputs, because these are in the input region. then these are also in the input region, such that their outputs are either less than the entire function or more than the entire function, respectively. So what does that look like? Once again, the picture will do the thinking for us. I have A, and I have B. It's a closed interval, very important. So I'm going to mark those sort of as closed, so everything in between and including. And I'm going to make a, once again, this is a nice differentiable curve, but it also would work if it were jagged, same basic idea, or even just a straight line. So here you can see that I have a value that's bigger than all the other ones, right? And that value looks like it's occurring right here. So that, in this case, would be point D. There exists some D in the interval A to B such that the output at that point, this point would be D comma f of D. The values there are bigger than or equal to everything else. Everything's below it, right? And conversely, you have a minimum value here at point C, and the coordinates there would be C comma f of C. And everything is greater than it for the entire function over the interval. There must be a max, there must be a min. Again, a simple idea, but an important one to state. It's a property of continuous functions. And more interesting than the statement of it itself is the sort of exceptions, the way this is phrased. There are two requirements, right? It's got to be continuous, and it has to be a closed interval. And it's worth exploring why those two requirements are so important, because it actually connects the idea of a limit. Why is it important for it to be continuous? Well, let's think of it this way. Let's say we had a specific example, and we had a function going from 1 to 7, and the function looked something like this, but it was not continuous. It had these removable discontinuities. Then, what could you really say was the max or min value? Let's say at 2, which is where this hole appears to be, it's not drawn the scale, you get the idea. Let's say the function spat out an output of 9. Could you say that there was a number that was always bigger than all the rest? Well, let's see. Because I don't have a value at 2, at 1.9, I would get maybe 8.9. And 1.99, I get maybe 8.99, so that's even bigger. And 1.9999, I get maybe 8.9999, it's even bigger than the last one. So we don't have this extreme value, do we? And the exact same thing is true for the minimum value. Maybe let's say it's 6. The closer I get to 6, the smaller my number becomes. And I don't have this minimum value because I can't get to 6, because at 6 there's nothing. The same is true for our endpoints. So if I had an open interval, meaning I was not considering what was happening at A or B, so let's say 1 and 7 again, and let's say my function was strictly increasing here, but I didn't have these endpoints included. I was limited to the open interval between 1 and 7. Then my minimum value looks like it would occur at 1, but the closer I get to 1 from the right, I'm always going to get lower and lower and lower. Like let's say this is 1 comma 0.5. Then the closer I get to 1, like 1.0001, which is like right around here, that would take me to 0.50001. And the closer I get, the lower I get. There's no minimum. And the same thing is true the closer I get to 7. 6.99999 produces maybe, let's say, 7.9999. But the closer I get, the more close I get to 8, but every number is successively larger. And as such, there is no unique extreme value. So for this reason, you must have a continuous function, and it must be on a closed interval. Otherwise, you get these exceptions. So with all that said, hopefully the stage is set for some interesting explorations regarding the continuous functions and their qualities as we start getting into some differential calculus. But for now, that's all. Hope it helps.